We have to have a little talk now about how different substances behave in solution, because that affects how we talk about reactions. Right? We can categorize substances very differently depending on some of their solution properties. So let's start with electrolyte and non-electrolyte. This is probably going to be the most important distinction that we make between types of substances when dealing with reactions. So electrolyte is a solute that causes a solution to conduct electricity. Okay? Pure deionized water does not conduct electricity. Okay? The reason people can get electrocuted in the bathtub or in a lightning storm or something like that is because you're not swimming in pure deionized water, of course. Right? So water, H2O, deionized pure water, is a non-electrolyte. Okay? That is a solute that does not cause a solution to conduct electricity. So take a look at these two diagrams right here. We've got a circuit. It's essentially an open circuit, because we got the two electrodes pointing down into the solutions there with a battery, and it's hooked up to a light bulb. Okay? And again, starting with just deionized water, that will not conduct electricity. Okay? We said before, deionized water is a non-electrolyte. Okay? Adding salt versus adding sugar gives a different outcome to these. Only one of those will conduct electricity. Anybody know which one? The salt solution will conduct electricity. So here, drawing a little light bulb that's bright over here. Okay, that conducts. Okay. Oh. The sugar solution does not. That's a simple experiment you can do yourself with a 9-volt battery and a little Christmas light or something like that. Okay? That's a fun little thing to do. Okay? You can actually go around and test various different solutions to see whether they are electrolytes or non-electrolytes. But yes, salt will completely conduct electricity. It will do it very effectively. Okay? It'll have, you can talk about the resistance and stuff. It'll have a very low resistance. So what that means, NaCl is an electrolyte. Sugar is a non-electrolyte. Now, look at those two formulas. Look at NaCl versus C12H22O11. Those fall into the two different types of compounds that we talked about in the last chapter, right? What type of compound is NaCl based on what kind of elements it's made out of? So, molecular. Is NaCl molecular? Think about it. What's the difference? How can you tell whether something is molecular or not? Where do the elements in a molecular compound come from? Okay, those are nonmetals only. Okay, so we've got C12H22O11. We've got it made out of C and H and O. Those are nonmetals. Okay, so here we've got the molecular compound. Okay. NaCl. Sodium is a metal. Chlorine is a nonmetal. Right? You can peek at a periodic table if you need to. But sodium's in group 1, chlorine's in group 7. Okay, over on the right. Okay. Metal and a nonmetal. And when it's metal and nonmetal, what kind of compound is that? Okay, so that is the big difference right there. Okay? Ionic compounds, if they dissolve, okay, we're going to say here, soluble ionic compound. Soluble ionic compounds, when dissolved in water, will cause that solution to conduct electricity. Okay? Molecular compounds, no matter how well they dissolve, okay, whether they dissolve or not, they will not help conducting at all. Okay? So look at NH4Cl and think about that carefully. Is that an ionic compound or a molecular compound? I heard you say ionic. What makes you think that's ionic?
At first I thought because of the hydrogens over there, but I forgot that it's...
Yeah, hydrogen is a nonmetal. Okay? So they are all nonmetals, NH and Cl, they are nonmetals. Okay? But you're actually right, it's ionic. Why is NH4Cl ionic? Okay? You need to know about polyatomic ions. One of the main reasons that you're supposed to memorize your polyatomic ions is so you can recognize them. Which polyatomic ion is in this compound right here? Yeah, we have the ammonium ion. This is ammonium chloride. Ammonium is NH4 plus, chloride is Cl minus. Okay, so that's ionic. Would you predict NH4Cl to be a electrolyte or a non-electrolyte? Yeah. Absolutely it is. C3H6O is a formula that could represent a number of different molecules. There are lots of ways to connect 3 C's, 6 H's, and an O, but any one of those would all have the same behavior for this. What would it be? Yeah, these are non-electrolytes. One example of that would be acetone, which it's a liquid that dissolves in water, okay, but completely non-electrolyte. If we started with deionized water, no conducting electricity. So we'll go somewhere important with that next time, but it's important we know that difference right away. We talked about the difference last time between electrolytes and non-electrolytes. What is the main observation that happens that's different between electrolytes and non-electrolytes? What do electrolytes do? Yeah, they cause electricity to be conducted through water. Okay. The reason for that is that if something is an electrolyte, electrolytes dissociate into ions when dissolving. Dissociate means break apart. So what we have with something like NaCl, which is an ionic compound, when we dissolve it, I'm just going to put water up here above the arrow, because it's not really a reaction with water, but it's just dissolving. What we actually end up with are sodium ions dissolved and chloride ions dissolved. Okay?
Would it be Cl2?
No, chloride ions. Chlorine, pure chlorine, the element is Cl2, but chloride Cl minus ions are just individual like that. So that's what happens when an ionic compound dissolves in water. Its ions come apart. And if you look at this little figure here, you can sort of see what happens. Let me zoom in on this a little bit. What happens is water molecules approach the ions on the outer surface of that solid, and the water molecules start to group around them and pull those individual ions off of the surface, after which they can be surrounded by the solvent particles. So let's put a couple of steps here. Ions separated from the solid. Oops, don't do that. And then, there we go. The ions are surrounded by water molecules. And it's these ions, like those. There's a plus ion, there's a minus ion. It's those ions in solution allow electricity to be conducted. The way it actually works is that each ion will be attracted to an opposite electrode. Right? The negative ions are going to be attracted to the positive electrode, the positive ions, vice versa. So that motion of ions towards each of those individual electrodes is actually what allows the circuit to be completed. If we've got at the negative electrode, you have a sort of an excess of electrons there that can be donated into the positive ions, okay? And then the negative ions are attracted to the positive electrode. They can actually give their electrons away to that positive electrode, and that continues the circuit. Okay? So that pattern of electron transfer within those ions, but it has to be ions in the solution in order to allow electricity to be conducted. Non-electrolytes look entirely different when they're dissolved in water. If we have a sugar solution, okay, sugar is molecular. There is a molecule. We just have individual molecules being surrounded by the solvent particles. We don't have positive ions and negative ions that can allow that electron transfer to happen between the electrodes to complete the circuit. Okay? So that's the key distinction here in solution behavior between ionic compounds and molecular compounds. And ionic compounds have these charges within the solution, whereas the molecular compounds do not. Acids also have some similar behavior to this, and we're going to talk a little bit more about acids later. We talked before about naming acids. We sort of identified them by the H at the beginning of the formula. The behavior of acids is interesting because it's a molecular substance. Okay. Right. Non-metals only. Most molecular substances just stay as molecules when they're dissolved. Okay? But acids are molecular substances that dissociate when dissolved to release H+ ions. So acids are interesting. They start as molecules when they're pure, but when they're dissolved, they break apart into ions. Okay? So an acid can be considered a strong electrolyte. Okay? Just like how sodium chloride dissolves into sodium ions and chloride ions, just like we said before. Okay? HCl, when it is pure, it's a gas, but when it's dissolved in water, it will cause that solution to conduct electricity. Okay? Hydrochloric acid will. So what do you suppose is actually being formed within that solution of aqueous HCl? What do you think? If it conducts electricity, what do we have to do to that HCl molecule? What do you think? Break it into its ions? What would the first ion be? H plus AQ and Cl minus. Okay. So NaCl is a soluble ionic compound. It's an ionic compound that dissolves. Okay? Soluble ionic compounds are strong electrolytes. HCl is called a strong acid. It's an acid that is also a strong electrolyte. Okay? Dissociates completely into ions. Oops, into. Not all acids behave that way, however. Okay? HCl is considered a strong acid, so it is a strong electrolyte. Okay? There are some acids that are considered weak electrolytes. Okay? This is acetic acid. We're going to see a lot of acetic acid in our examples coming up. Acetic acid is the active ingredient in vinegar. In our acid-base titration lab, you're going to titrate the acetic acid in vinegar. Okay? So it is considered a weak electrolyte because it does not completely dissociate into ions. Okay? It makes a small, right? It makes a fairly low concentration of ions. But weak electrolytes, like acetic acid, exist mostly as the intact molecule. Okay? So, by this point, we've talked about strong and weak electrolytes. Okay? The strong electrolytes completely break up into ions. Okay? They make the solution strongly conductive to electricity, so a light bulb will burn bright, okay, in a strong electrolyte solution. Weak electrolytes do form some ions, but not much. Okay? They mostly stay as the intact molecule. So weak acids. This is a weak acid. Weak acids are pretty much the main weak electrolyte that we will talk about. Okay? So what do you suppose a light bulb would look like if the circuit was a weak electrolyte solution like that? Yeah. If you had enough voltage, you could get a dim bulb from that. Okay? A decent strong electrolyte will be just like a short circuit, essentially. Okay? Weak electrolyte will have a good amount of resistance because there's only a small amount of ions in there. Okay? So weak electrolytes and strong electrolytes conduct electricity. They contain ions in the solution, just the difference is how many ions. Right? Non-electrolytes are things that have no ions in solution, like molecular substances. Okay? Back here, I called NaCl a soluble ionic compound because not all ionic compounds dissolve in water. The ones that do dissolve in water are strong electrolytes. Sodium chloride totally dissolves in water. It makes the solution completely conductive. Okay? Ionic compounds that do not dissolve, they remain solid in their ionic lattice when added to water. So look at the difference between silver nitrate and silver chloride just in these little pictures here. We could start with solids of either one. Okay? Pour them in water, stir it up a little bit. The silver nitrate would completely dissolve, which means the plus and minus ions separate from each other, makes those free positive and negative ions in solution that allows the solution to conduct. Okay? Silver chloride will never dissolve in water. It remains in its ionic lattice, and we'll have little to no ions free in the solution. Okay? So if we've poured silver chloride, it won't actually make a solution. It'll just sort of settle down to the bottom. Okay? Think of pouring chalk dust or sand or something like that in water. You can maybe suspend it for a little bit, but it'll settle, and it's not truly dissolving. Okay? So we have this table of solubility rules, which you saw a little bit of in lab when you were writing balanced chemical equations for things. This chart of solubility rules will be given to you on exams. It will be in a form without the formulas in parentheses. Okay? So I reminded you here what nitrate and acetate and sulfate and stuff like that are. Those little formulas will not be present on the exam, but the whole rest of this chart will be. And it's pretty straightforward. If something is soluble in water, something fully dissolves in water, what phase label will you give it? Yeah, AQ. Okay, that's the phase label for something that's fully dissolved in water. Okay, so you identify one of the ions. If you see one of the ions over here, you have to make sure to look across to see if the other ion makes that compound an exception to the solubility rule or not. Okay, so most chlorides, bromides, iodides are AQ. Okay, unless they happen to be paired with silver, mercury, or lead. That makes a compound insoluble. When something is insoluble, what phase label does it have? Yeah. Just like our silver chloride right here. Most chlorides are soluble unless it's paired with silver. That makes it insoluble. Okay? That's why this has a solid phase label. Okay? And the whole bottom half of the chart is opposite. One quick thing to look at here, your textbook simplifies this a little more than it probably should be. But specifically, what I want you to look at here, when hydroxide pairs with calcium, strontium, or barium. Calcium hydroxide, strontium hydroxide, barium hydroxide, it is slightly soluble, but what we'll actually be able to do is use this for many purposes. These are considered insoluble. So you probably noticed in your reactions lab, I think you did a calcium hydroxide as a product. Okay? If you just called it slightly soluble or whatever, you may think it was AQ, but it tends to be concentration dependent, okay? And most normal, reasonable concentrations would make those precipitate. Okay? So for pretty much any time you encourage it, or you encounter it, I suppose, I would consider calcium, strontium, or barium hydroxide to be insoluble. Okay? So those are still over here. Okay? But the rest of these, okay? So if you take second semester general chemistry, we'll talk about solubility equilibria. There's a way of quantifying that very small amount that does get dissolved, and there are things that influence that, like concentration, and there are entire conversations to be had about that. So